What if I told you that there is a colossal structure that begins at the edge of our solar system, one that encircles our sun and all of the planets, but we've never seen it? A shell made up of billions, or even trillions of ancient icy chunks, the size of mountains, marks the outermost boundary of our solar system, or so we think. Jaw-droppingly far away, beyond the reach of even our most powerful telescopes, the Oort cloud is a region shrouded in mystery and speculation where the sun's influence grows faint as it brushes up against the void of interstellar space. What exactly is this Oort cloud? If we've never directly observed it, how do we know it's out there? And why do some people question its existence? Let's find out. Join me today as we venture to the farthest reaches of our solar system and beyond, to construct an image of this unseen astronomical wonder. You've probably heard of the asteroid belt, and maybe even the Kuiper belt, at two different locations in our solar system. These roughly donut-shaped bands of debris each move in the same direction, and more or less on the same orbital plane as the planets around our sun. The asteroid belt is closest to the sun of these two debris rings, located between Mars and Jupiter, and consists of millions of orbiting asteroids. The Kuiper belt, on the other hand, was first proposed by astronomer Gerard Kuiper as the origin of short-period comets in the mid-20th century. It is a massive field of icy debris out past Neptune. Occasionally, a piece of Kuiper belt debris will get pushed by gravity, sending it on a new orbit closer to the sun. In some cases, this creates a new short-period comet. These comets have orbits of less than 200 years, and are often predictable as they continue to make subsequent orbits around the sun. At the same time that Kuiper was investigating short-period comets, a Dutch astronomer named Jan Oort was contemplating the origin of long-period comets. Few scientists of the 20th century made more contributions to astronomy than Oort. In 1927, he calculated our place in the Milky Way galaxy, and in 1932, he was the first to find evidence of dark matter. To name a few examples of his discoveries, in 1950, Oort was the first to theorize the existence of a thick bubble of swarming icy debris that surrounded our entire solar system, now known as the Oort cloud. But unlike the asteroid belt and Kuiper belt, it's still yet to be directly observed. To understand this theory, let me explain what led Oort to this proposition. Unlike comets with short orbits, long-period comets were unpredictable. For one thing, their orbital periods were so long that in some cases they could take as many as 30 million years to complete one orbit. And, curiously, these comets came from all different directions and had various orbital inclinations. It was a mystery on the grandest of scales, but Oort noticed a few things that all of these long-period comets had in common. Their orbits indicated that these comets weren't coming from far out in interstellar space, but that their origin had to be closer to home. However, not too close to home. So if these long-period comets weren't coming from the Kuiper belt, and weren't coming from far out in interstellar space, where were they coming from? Oort found a peculiar similarity among the orbits of these comets, one that might just provide the answer to that question. The point in a comet's orbit where it is most distant from the sun is called the aphelion. Oort noticed that all observed long-period comets seem to have aphelia that all grouped around a certain distance, around 7.5 trillion kilometers from the sun. That's right, trillion with a T. As you can see, when it comes to the distances I'll be talking about in this video, our typical units of measurement fall a bit short. So, instead of using kilometers, I will switch to astronomical units. 1 astronomical unit, or O, is defined as the distance between Earth and the Sun, or about 150 million kilometers. So Earth is 1 astronomical unit from the Sun. The aphelia grouping that Oort noticed, where the long-period comets reached their farthest orbital distance from the Sun, was about 50 O. To help picture the orbits of these long-period comets, keep in mind that the outermost planet in our solar system, Neptune, is around 30 astronomical units from the Sun, or about 4.5 billion kilometers. The main region of the Kuiper Belt extends from Neptune's orbit at 30 astronomical units out to around 50 astronomical units. But recent evidence from NASA's New Horizons spacecraft suggests a second region of the Kuiper Belt called the scattered disk, which continues to around 1,000 astronomical units. It's with these key findings from observed comets that they didn't come from far out in interstellar space. The orbital distances clustered around 50,000 astronomical units, and the fact that they arrived from any direction and orbital inclination, that Oort theorized a roughly spherical swarm of icy debris that he believed to be the origin of long-period comets. In the years since then, mathematical models have shown agreement with the Oort cloud theory, and astronomers have further theorized various mechanics by which the Oort cloud came to be in its current state. The leading idea is that the Oort cloud formed from ancient debris, leftovers from when our planets formed 4.6 billion years ago. After the planets formed, the surrounding area was still rich with these smaller, leftover chunks of material called planetesimals. The gravity from these early planets then scattered the leftover material in every direction. Some material was flung out of the solar system entirely, but a significant portion was sent into seemingly random, eccentric orbits around the Sun. These scattered planetesimals had eccentric enough orbits that they were influenced by gravitational forces outside of our solar system, while still remaining captured in our Sun's orbit. And it's believed that this is how these billions or trillions of icy chunks came to be part of the Oort cloud. Gravitational perturbations can force Kuiper Belt objects out of place, creating short-period comets. We think that similar forces are what send Oort cloud objects into elliptical orbits with the Sun, thereby creating long-period comets. These perturbations could be caused by passing stars or molecular clouds, or tidal forces from the Milky Way itself. In fact, about 70,000 years ago, Scholz's star gained the title of the star that came closest to our solar system, actually grazing the outer region of the Oort cloud. But, luckily for us, it didn't cause any catastrophic disruptions to the Oort cloud or our solar system at large. Scholz's star is a low-mass binary system made up of a red dwarf and its brown dwarf companion. So 10 millennia ago, even at a much closer distance to the Oort cloud, the gravitational influence of this binary star was significantly weaker than that of our much more massive Sun. However, while most objects experienced little to no impact, during the low-mass star's brief encounter with the edge of the Oort cloud, numerical simulations from 2018 concluded that Scholz's star is believed to have nudged at least some objects out of place, creating and influencing the trajectory of some long-period comets. But the Sun has been around for over 4 billion years, and that's a lot of time for other close encounters with stars in the distant past. Could these interactions have prevented the Oort cloud from forming? Our models suggest no. However, Oort cloud material may get exchanged with passing stars over eons. You see, more recent numerical simulations have suggested that Oort clouds could exist around other stars. Our Oort cloud may also have both an inner and an outer region, each with its own distinct shape. Some scientists suggest that the inner region may be more like a disk, similar to the donut shape of the Kuiper Belt, while the outer region is suggested to form the spherical shell more widely associated with the Oort cloud. Altogether, the inside edge of this region Oort cloud may be 2,000 astronomical units from the Sun at its closest, with the far edge stretching all the way out into interstellar space, potentially reaching as far as 100,000 astronomical units from the center of our solar system. That means the Oort cloud could extend more than 1.5 light-years across. To put that into perspective, since we're talking about very, very large distances, consider the Voyager spacecraft for a moment. As of the publication of this video, Voyager has traveled to a distance of about 139 astronomical units from the Sun since its launch from Earth at 1 astronomical unit in August of 1977. That's about 3.3 astronomical units per year, or about 56,000 kilometers per hour. It's the second farthest human-made object in space, just after Voyager 1. In August 2007, Voyager to pass beyond the boundary of the heliosphere, the outermost layer of the Sun's atmosphere. It extends out beyond the planets, and 3 times farther than the distance to Pluto. Outside of the heliosphere, the Sun's constant flow of charged particles, called the solar wind, is finally impeded by the interstellar medium, and in November 2018, Voyager to finally crossed the final layer of solar turbulence called the heliosheath, and continued on into interstellar space. Despite passing beyond the heliosphere, and well past the main Kuiper belt, Voyager 2 would still need to travel for another 300 or so years just to reach the innermost edge of the Oort cloud. That's how far away it is, and to fly through the Oort cloud, that could take another 30,000 years. Even when traveling at 56,000 kilometers per hour, it still takes all that time to travel around 1.5 light years. If you've ever wondered why interstellar or intergalactic space travel is difficult, keep in mind that our nearest stellar neighbor is Proxima Centauri at around 4.5 light years away. However, some still question the existence of the Oort cloud, mainly because we're unable to directly observe it. Another argument has been made that long-period comets may come from other places, such as interstellar space. And in fact, the first observation of an interstellar comet, one that had origins from outside our Sun's influence, was made in 2019 by amateur astronomer Gennady Borisov. Professional astronomers joined in to collect data on Comet I, Borisov, named after its first observer. They found an unusual composition, a higher concentration of carbon monoxide than the average comet originating from our own solar system, suggesting that this comet may have formed in the presence of a red dwarf, a different type of star than our Sun. And yet, the vast majority of astronomers agree that the Oort cloud is really out there, despite the fact that we've never laid eyes on it. Plenty of indirect observations and mathematical models show great support for the theory, and the evidence continues to add up. But why is it, exactly, that we've never been able to see the Oort cloud? After all, with telescopes, we can see stars far beyond our own solar system, and even the shapes of distant galaxies. The difference is size and light. Think about it. A piece of Oort cloud debris is roughly the size of one mountain on Earth. Let's consider Mount Everest at around 9 kilometers tall. Now consider the Oort cloud's innermost boundary begins somewhere around 3,000 astronomical units, or roughly 450 million kilometers from the Sun. The distance from the Sun to the nearest piece of Oort cloud debris is 50 million times the size of the debris. Talk about looking for a needle in a haystack. But more crucially even, is that stars and galaxies give off light, but Oort debris does not. The planets are relatively close to the Sun, so they're able to reflect the Sun's light and therefore are visible. Likewise, the asteroid belt and even the Kuiper belt are close enough to the Sun that we can use telescopes to directly observe their debris. But outside of the heliosphere, the Oort cloud is just too far and too dark for our telescopes to catch a glimpse. Despite the Oort cloud's gargantuan footprint and pivotal role in shaping our understanding of the origin of many long-period comets, for now, we can still only infer its existence through mathematical models and indirect observation. But don't let our inability to make direct observations discourage you from following the evidence. I can think of a few other times in history when scientists put forth monumental theories, despite a lack of direct observation. For example, in the 16th and 17th centuries, respectively, Copernicus and Galileo each put forth the theory that the planets orbited around the Sun, contradicting a widely held belief at the time that the Earth was the center of the solar universe. Their theory of a heliocentric solar system was not based on direct observation, but rather on indirect observation of the orbit of the planets. As we know, that theory turned out to be spot on. That's one thing I love about science and the pursuit of knowledge. There's always more to learn. The more questions we ask, the better our understanding of the solar system will get. Who knows? Maybe in 100 years, the future astronomers will have found a way to prove the existence of the Oort cloud once and for all. Or maybe they'll have found a whole new explanation for long-period comets. Until then, the Oort cloud remains one of astronomy's most compelling enigmas. Thanks for watching.